How is angular momentum defined for a rotating object? What equation define it? What units is this measured in? So angular momentum L is equal to the rotational inertia times the rotational velocity. If rotational inertia is mr squared and the rotational velocity can be calculated as v over r, we essentially have m times r squared times v over r. Well, the square cancels the r on the bottom, and we really have what looks like mrv or mvr is a way to calculate we're going to get to as well, but that's going to help us lead to our units, kilograms, meters square over seconds. So it's just derived by what you're multiplying. How is angular momentum defined for an object which is not rotating, point particle moving in a straight line? We're going to calculate that as mvr, mass of the object moving in a straight line, multiplied by its linear velocity, multiplied by r, or the radius. And our radius is distance between the line of action, the line that is in motion, the line that it's going to be moving across, and how far that line is from the system's pivot point. So r is the distance between the line of action and the system pivot point. And we can see that we got the MVR. It was kind of resolved or derived in number 1. How is the angular momentum of a point particle a relative measurement? Explain completely. The angular momentum of any object must be taken about a specific pivot point, and it's different for different pivot points. So depending on the pivot point, that's why it's a relative measurement. How is angular momentum changed? How has anything changed? An unbalanced external force, but in this case, because it's angular, an unbalanced external torque. We know from Newton's first law says an object in motion wants to stay in motion, object at rest wants to stay at rest. Objects want to do what they're doing, and the only way to change them is an unbalanced external torque in this case. Explain why a figure skater rotates faster when she pulls her arms in closer to her body. Think of the Olympics. When they pull their bodies in, they're changing the distribution of mass and they start to spin faster. When they want to slow down, their arms go further out. So in this case, her angular momentum remains constant. She is free to spin. Of course, the angular momentum is constant because there's not been any external unbalanced torques acting. Her rotational inertia is small or smaller when she draws her arms in, so the angular velocity increases. So knowing the angular momentum is constant, if the rotational inertia goes up, the angular velocity will go down. Or, again, the angular momentum is constant, so if the rotational inertia decreases, the angular velocity will increase. They are reverse or indirectly proportional, reverse proportional. If one goes up, the other goes down. How does a diver control how fast he rotates as he falls through the air? Must be a skydiver, right? By changing his rotational inertia. We got that from the previous question. If he pulls his arms and legs in, this will reduce the rotational inertia because the radius essentially is smaller. Reducing the rotational inertia will increase the rotational velocity, just like what we saw with the ice skater, the figure skater. A student stands on a small frictionless platform which is free to rotate. He holds a bicycle wheel in his hands, oriented so that the axle of the wheel is vertical and the wheel itself is horizontal. He pushes the wheel clockwise, causing it to rotate rapidly. What change will be observed in the student? Explain completely in terms of momentum. And it does say try it. We do have this equipment in our school laboratory. So if the system as a whole has an angular momentum of 0 before anything begins, and then the student, which is an internal component, spins the wheel one way, and he's standing on a platform that's free to rotate, we should see a rotation in the opposite direction. That way, once you add up the individual wheel and then the student on the disc, they should add up to be 0 because momentum is going to be conserved. So here we've written the student will begin to spin in a counterclockwise direction, which is opposite of what he spun the wheel. The total angular momentum of the system will remain constant. It'll remain at 0. If the wheel rotates one way, the system must rotate in another way to compensate it. So what do you think would happen if he flipped the wheel over while he's holding it? He's holding it on the axle. If he flips the wheel over, the wheel's now going in the opposite direction. The student, the system, should slow down and then reverse direction from the platform he's standing on because it needs to maintain a total overall, once you add it up, angular momentum of 0 because that's where it started and there's been no unbalanced external torques acting. A frictionless platform has a mass of 40 kilograms and a radius of 2 meters and can be considered a solid cylinder where the rotational inertia is 1/2 mr squared. The platform initially rotates at 10 radians per second counterclockwise. We're going to call counterclockwise positive, clockwise negative. Calculate the angular momentum of the platform. We've got the mass is 40 kilograms, radius is 2 meters, I equals 1/2 mr squared, and the initial angular velocity at 10 radians per second. We're looking for angular momentum. We're looking for L. We know that L is I omega. I is 1/2 mr squared. And omega, they told us it's going to be 10 once we put the numbers in. So 1/2 times 40 times 2 squared times 10. Put that into our calculator. We should get 800 kilograms meter square over seconds. A force of 30 newtons is exerted on a platform to the right, perpendicular to the radius as at a point 1 meter below its axis, over a period of 4 seconds. Explain how the angular velocity of the platform will change because of the force. What happens to the angular momentum of the platform during this time? They want us to explain and calculate. Well, the angular momentum of the system will increase. The force is an outside, unbalanced external torque on the system. The torque will cause an acceleration, which changes the angular velocity. And if there's a change in angular velocity, and there's only one object, we know that there's a change in angular momentum. And the only time we see changes in momentum is when there's an unbalanced external force when it's linear, a linear system, or an unbalanced external torque for a system that has rotation. All right, so let's calculate. We know that torque is equal to I alpha, or rotational inertia, times rotational acceleration. So if torque is I alpha, torque would also be I times the change in angular velocity over time, because alpha is the change in angular velocity over time. Well, if we put our I times delta omega together, we would have delta L, or change in the angular momentum. So we're going to say torque is equal to delta L over T, because we're taking the I and the delta omega together. And then if we multiply the T to the other side, we would say torque times time is equal to a change in angular momentum, because this torque is an unbalanced external torque, so we know it's going to give us a change in angular momentum. Let's plug in our numbers. 30 newtons times 1 meter times 4 seconds is our change in angular momentum. 30 times 1 times 4 would be 120. And then our units for angular momentum would be kilograms meter square over seconds. How could the force be modified to create a greater change in angular momentum? Well, the force is essentially giving us a torque. So how do we calculate torque? What influences torque? If we increase the force, yes, that would give us a greater torque, a greater change in angular momentum. Torque is a force times the distance from the pivot. So if we increase that distance from pivot, it would also increase the torque. So changing the value of the force, or changing the value of essentially the radius, if we make either of those bigger or both of them bigger, we would get a greater change in the angular momentum. A bar of uniform density is secured at its center of mass and rotates with a clockwise angular velocity of 4 radians per second. So we know our initial angular velocity is 4 radians per second. The bar, I equals mr squared, so we know that the rotational inertia formula for the bar has a mass of 8 kilograms and is 0.5 meters long. So the length of it is 0.5 meters. I think I'm going to end up putting R, and then I'm going to change it to L so that I know that the length, not the radius, but the length of it, because it's rotating at the center. When the rod is horizontal, a downward force is applied for 0.2 seconds to the right edge of the bar, speeding it up to an angular velocity of 12 radians per second. So after our 2 seconds of time, let's make that radius an L, because that's the length, that's not the radius. Then we've got a time of 2 seconds, and then the final angular velocity would be 12 radians per second. We're going to calculate the magnitude of that force. Well, from the previous problem, we said that torque times time is equal to a change in angular momentum. It seems like a pretty good formula for this based on what we have. Now on this, I've put -4, -12, because clockwise is negative, counterclockwise is positive. So torque times time is equal to the change in angular momentum. torque times time is equal to I times delta omega, right? The change in angular velocity. And then torque is force times displacement. And then times time is equal to I delta omega. And then on the next line, I just want to divide the distance and the time to the other side. So that way we've got everything solved for the force. I believe we can plug in the numbers. We have 8 times, because I is mr squared, we would have 8 times 0.5 squared times negative 12 minus a negative 4, or negative 12 plus 4, all divided by 0.25 times 0.2 squared. We do the math on the top. We get 16 on the top and 0.05 on the bottom. So the force is 320 newtons downward. That takes care of the negative. Last question on the page, number 10. An arrow of mass 2 kilograms moves at a velocity of 20 meters per second to the right along the dashed line. Rank the angular momentum of the arrow about each of the points, and then justify the ranking. Well, first let's just say that the angular momentum of the object moving in a straight line is calculated as MVR, mass, velocity, radius, where R is the distance from the line of action to the pivot point. And we've got those pivot points at A, B, C, D, and E. A, B, C are very straightforward. It's just going to be mass times velocity times the radius. D is a little bit different. We've got to take a look at it's being sent at a 30-degree angle, and the distance is 2. So if we're wanting to look and see, well, what would the straight down line be? It'd be calculated as, that's the opposite side, so 2, the hypotenuse, times the sine of 30, and 2 sine 30 is equal to 1. So now we've got that calculation. And if we want to calculate each one, we're just going to look at the MVR for A, B, C, D, and E. All right, looks like we have our justification written out. The angular momentum of an object moving in a straight line is calculated as MVR, where R is the distance from the line of action to the pivot. They gave us a velocity of 20 meters per second. They gave us a mass of 2 kilograms. We just need to take that mass times the velocity times each of the radiuses. The MVR of the point A would be 2 times 20 times 2. So we have a value of 80. For B, looks like it should be the same thing. 2 times 20 times 2, which hasn't changed, it's still 80. For the third one, we would have 2 times 20 times 3, or 120. And then for the third one, our MVR would be mass of 2 times velocity of 20, and then the radius being that 2 sine of 30, or essentially 1, but we'll put it in the way that it should go. That should give us 40. And then E is 0, right? Because it's on the line of action, there is no radius. So C is our largest value. A and B are equal to each other. D is our smallest non-zero. And then E up there, that's our 0. Can't forget it. So we need to put E on the very back end, because it's essentially 0 sitting there. It is 0. An arrow of mass 2 kilograms moves at a velocity of 20 meters per second to the right. It strikes a wheel which is initially at rest and whose moment of inertia is 80 kilograms meters per second and radius of 0.8. At a point along its edge perpendicular to the radius, the arrow becomes embedded in the wheel. So after it hits, it's not flying past. So we've got MVR in the beginning, and then we've got the rotational inertia of the system afterwards. Calculate the angular velocity of the wheel after it is struck by the arrow. Assume that the arrow doesn't change the moment of inertia. So when the arrow is in the wheel, it's saying it's not affecting anything. So it's nothing to worry about once it sticks it. So we can say that the initial angular momentum is equal to the final angular momentum. The initial angular momentum would be based on the MVR of the arrow because the wheel's not moving. And then the final angular momentum will be based on the I omega of the wheel, disc, whatever this is, system. So the initial would be MVR, mass of the arrow 2 times its velocity 20 times the radius 0.8. When we put that into our calculator, we get 32. I was close. 32 kilograms meters squared over seconds. So that's the initial angular momentum. We know the initial angular momentum is equal to the final angular momentum, so we can set that 32 equal to the final. And how is the final based? It's based on the I omega of the wheel. And what did they tell us about the I omega of the wheel? So the moment inertia is 80, and we're looking for the omega, correct? So we know 32 is equal to 80 times omega. Divide that 80 to the other side. We get 0.4 radians per second is the omega of the wheel after the impact. Does the linear momentum change as a result of the collision? Now the linear momentum, if so, what force is responsible for changing the linear momentum? Yes, it changes because nothing's moving linearly after the impact. So there must be a change. And it's actually the pivot in the center of the disk that keeps the disk from moving linearly. I don't know if I'm inventing that word, but I'm going to say linearly. It's considered an outside force because it's holding on to the ground, right? If it didn't pivot, if that arrow hit it, it should have pushed the disk sideways. But because that pivot point is mounted such that it's holding on and causing a rotation and not a left or right motion, that's going to be our external force. A little bit tricky. How would the answer to A be different if the path of the arrow were shifted downward without changing the direction? So it's still moving horizontally. We're just going to shift it downward such that the arrow struck the wheel at point P. Well, if we look at the original drawing, we were hitting it at the top part at the outermost furthest point, 0.8 meters from pivot. Now we're going to be below the pivot point instead of above, and we're not going to hit it at the lowest point. We're going to hit it at something higher than that. So that line of action, as it comes across, it's going to be closer than the radius, the outermost portion. And that's the portion we look at. So first we're going to say, well, if we hit it at the bottom, wouldn't that cause the rotation to be counterclockwise? Because when we hit it at the top, from left to right, it would cause a clockwise rotation. So this time, now that we're hitting at a different location, we're going to cause a counterclockwise rotation. The second thing is that based on our MVR calculation, the mass of the arrow hasn't changed, the velocity of the arrow hasn't changed, but the radius of its line of action hitting from the pivot point is different. It's smaller. So it's going to have a smaller rotational momentum, angular momentum, I should have said. So it's going to be moving slower. So you have a smaller angular momentum will result in a smaller system velocity. So the angular velocity of the disk would be less than it was. A platform whose rotational inertia is 1/2 mr squared has a mass of 40 kilograms and a radius of 2 meters and can rotate without friction. A buoy of mass 60 kilograms initially stands on the edge of the platform. The platform rotates counterclockwise, so we'll say in the positive direction, at 10 radians per second. We want to calculate the angular momentum of the platform buoy system. So here's our little platform. This is a merry-go-round in the park. Its rotational inertia is 1/2 mr squared. The mass of the platform is 40. The radius where the buoy is standing is, what did it say it was, 2 meters. And then we're going to stick the buoy over there on the right side. There he is, standing on the right edge. And the buoy's mass is 60 kilograms. And we're all rotating at that our initial rotational velocity or angular velocity of 10 radians per second. If we're going to calculate the angular momentum of the platform buoy system, we're going to say that the L, the angular momentum, is equal to the total rotational inertia times the angular velocity. Because everything's rotating at the same speed, we don't have to distribute that omega into the parentheses. We can add up the i's and then multiply. If you prefer, you can do I omega plus I omega plus I omega, but all the omegas are the same. So we have the I of the platform plus the I of the buoy. The I of the platform, they told us, was 1/2 mr squared. And then the I of the buoy is just going to be mr squared because he's not physically rotating. He's spinning along the edge of the platform, right? So in that case, we're going to treat him as a point source. He's going to be mr squared. And if we carry that up, we would have L is equal to 1/2, and then the mass of the platform, 40, times the radius squared, so times 2 squared. So 1/2 times 40 times 2 squared plus the mass of the buoy, 60, times 2 squared because he's on the edge radius of the platform. Close the parentheses, and then we're going to multiply by that 10, the omega. And then we take the 1/2 times 40 times 2 squared plus 60 times 2 squared, add those up, and then multiply by 10. We get a number close to, I think it's 3,200 kilogram meters square over seconds. Just got to check it in the calculator. There we go. There's our 3,200. All right, the buoy slowly walks to the center of the platform until he is straddling the axis and has 0 angular momentum. What happens to the angular momentum of the buoy platform system? Let's take that one first. Was there an unbalanced external torque? I don't think there was. The buoy walking, that's internal to the system, so nothing has happened to the angular momentum of the system. It is conserved. Momentum is conserved unless there's an unbalanced external torque, unbalanced external force. There was not one. So the angular momentum remains the same. The buoy walking does not represent an outside torque to the system. What's the second question they ask us? What happens to the angular velocity of the platform? It asks us to explain and to calculate that. So do we suspect we're going to see something different with the velocity of the system, the angular velocity of the system, well, what has happened? The boy, who weighs more than the platform, has moved from the outside edge to the inside center. So the distribution of the mass of the system has changed, hasn't it? And if the distribution of the mass has changed, the rotational inertia has changed. The resistance to rotate has changed. And we know if the mass comes closer to the center, the rotational inertia is less, because essentially the radius of that mass is less. So if it resists rotating less, that should mean the velocity is greater, because I omega, the product of that, is consistent, it's constant. So if the I goes down, the omega has to go up, because the L is constant. So the angular velocity increases. The rotational inertia of the system decreases because the mass of the boy moves to the center. This causes the angular velocity to increase. It's all about the distribution of the mass, right? Well, and the mass itself. They do want us to calculate what the velocity is going to be now. And we can say the initial angular momentum is equal to the final angular momentum. We want to start back as far as possible, so we can start with something that we know, something that we're secure with. So the initial angular momentum is equal to the final angular momentum. And if the initial angular momentum, we know what that is, don't we? Didn't we just do number 12a? We know it's 3,200. So we know that 3,200 is equal to the final angular momentum. We just then need to figure out, well, what is the omega, the angular velocity? Well, if it's 3,200 is equal to the final angular velocity, we can say that the rotational inertia of the platform plus the rotational inertia of the buoy times omega is equal to 3,200. Now the rotational inertia of the platform is 1/2 mr squared, and the rotation of the buoy is mr squared. Now if he's standing at the center, what's his r? It's 0, isn't it? So does the buoy have a rotational inertia? No, he does not. So that means the 3,200 is equal to 1/2 mr squared from the platform times omega. The platform mass is, what is it, 40? And then the radius is 2, so 1/2 40 times 2 squared. Get that taken care of. Divide 3,200 by that value, and that solves for omega. And when we do the math, I believe it's 40 radians per second is the angular velocity of our platform. Last page. The platform is brought to a rest, so we know the angular velocity is 0. And the buoy is returned to the edge. The buoy returned to the edge. The buoy then runs along the perimeter of the platform clockwise. So he's running along in a negative direction. He's still on the platform, running, with a constant linear speed of 6 meters per second. We want to calculate the angular velocity of the platform and indicate its direction when the buoy is running and then when the buoy stops. So let's put the buoy's speed in terms of omega, which would be 3 radians per second, because we know we're going to take his linear speed and divide by the radius. And I'm going to call it -3 because he's moving in a negative direction clockwise. The buoy is running, so let's just say that the initial angular velocity is equal to the final angular velocity. If the system was brought to a rest, the initial angular, momentums. The initial angular momentum is equal to final angular momentum, so 0 is equal to the I of the P times omega of the P, plus the I of the B times the omega of the B. P is platform, B is buoy. And they're separate now because the buoy's running, the platform's rotating. He's not stuck to the platform, so they have different omegas. I'm going to subtract the platform side to the other side. So I've got negative IP times omega P is equal to IB times omega B. So I've got negative 1/2 mr squared, or 1/2 40 times 2 squared, close parentheses, times omega, which we're looking for, is equal to the I of the child, which would be mr squared. Mass of the child is 60, times 2 squared, because he's on the outside edge, times -3, because that is his velocity. He's moving at -3 radians per second. If we do the math on the left side, 1/2 of 40 is 20 times 4 would be negative 80 times omega. Check it with a calculator. Negative 80 times omega is equal to 360. Let's see, 4 times. No, that's not going to be right. Better get a calculator. Negative 720. And then if we divide the negative 80, negative 720 divided by negative 80, so moving the negative 80 to the other side, we're going to get the angular velocity of the platform. Which would be 9 radians per second. And it's positive, so we know it's going counterclockwise. That's the first question. The second question is, if the boy stops running, if just after the boy stops running, what is the velocity of the platform? Well, if the boy's not running, there's nothing going in the clockwise direction. And if the total angular momentum of the system has to be 0, if there's nothing going clockwise, what can you have going counterclockwise? Nothing, because it has to add up to be 0. The initial angular momentum was 0, so the final angular momentum, when you account for everything and add it all up, has to be 0. So the boy going in the negative direction, going down to 0, means everything going in the positive direction also has to go down to 0. So the initial angular momentum was 0, so the final angular momentum must be 0. And the only way that can be true is if the platform's not moving, in this case. Number 13, we've made it to the very end. An experimental cannon is constructed out of a solid sphere with a small muzzle on its top, which launches a cannonball perpendicular to the sphere's radius as shown below. The sphere has a moment of inertia of 100 and a radius of 1.5. After launching the cannonball, mass of 2 kilograms, the sphere rotates at 2 radians per second about its center. Calculate the velocity of the cannonball after the launch. So let's just fill some things in. So we've got on our picture, eye of the cannon is 100. The radius of the cannon was at 1.5. Yeah, that's it. What other information they give us? Didn't they give us the mass of the ball? Yeah, the mass of the ball is 2 kilograms. And then the rotational velocity of the system after it's launched is going to be 2 radians per second. All right, the initial angular momentum is equal to the final angular momentum before the cannon is fired. Do you think it's moving? It's probably not. It's probably sitting there all chill. They've loaded it up. They're lighting the fuse. So the initial angular momentum is definitely equal to the final angular momentum. But what do we think the initial angular momentum is? It's most probably 0. So if the initial angular momentum is 0, the final angular momentum must be 0. So whatever angular momentum we get from the cannonball going to the right must be equal, but in the opposite direction of the angular momentum of the cannon rolling as it recoils backwards. Right? It's going to start to spin a little bit counterclockwise. So we're going to set this up as saying the initial is 0, and then the final is going to be calculated as the angular momentum of the ball plus the angular momentum of the cannon. The ball's not rotating, so we're not going to use I omega. We're going to use MVR. And then the cannon would rotate because it's a big ball, so we'll use I omega for it. So the MVR of the cannonball, 2 times 1.5 times V, plus the I omega of the cannon, which would be 100 times 2. When we add those up, we should get 0. So 3V plus 200 is equal to 0. If we subtract 200 to the other side, negative 200 is equal to 3v, and then divide both sides by 3 so that we're solving for v, the velocity. We would essentially get, in this case it's showing it'd be negative 66.67 meters per second. Again, negative is just directional. But we can just restate the negative as the direction is to the right according to the drawing we were given.